So welcome to the 10th part of A2, where we're looking at linear momentum. Just to scroll up a bit, we can see that we have the notes from the first topics relating to impulse and momentum, right? Those are the previous two videos. And overall, this is the 10th part of topic A2, which is overall linear momentum and impulse. Now, the question that we're going to look at in this video will be one question, and it'll be a nice review question combining a variety of topics. And let's take a look. So we're given that we have a wall, a bullet is being fired, right? So we have this 2-gram bullet is entering the wall at a speed of 180 meters per second. It becomes, right, it'll eventually become embedded in the wall. And the wall itself is exerting a force against the bullet of 750 newtons. Calculate the bullet's change of momentum. So change of momentum, we remember, is impulse, which is J, or the change of momentum is equal to the mass times the change of velocity. And we can just plug in now that we know that we have this 2-gram bullet, which is going to be equal to 0.002, it's 0.002 kilograms, right? So for our units for momentum and impulse are kilograms meters per second, or Newton seconds. So it's 0.002 kilograms times the change in momentum, or the change of velocity. We went from 180 meters to 0, right? It enters at 180 meters and eventually comes to a stop. That's a difference. That's a change of velocity of 180 meters per second. And if I multiply this out, we see that it comes out to 0.002 times 180, it comes out to 0.36. So this is our final answer is going to be 0.36 kilograms meters per second. And the other unit, which might be helpful here, is 0.36 Newton seconds. It should become, right, the Newton seconds should become a useful unit now when trying to calculate the time, because we're told that or we're asked to find what is the time taken for the bullet to stop, given that we have this change of momentum of 0.36 Newton seconds. We could solve this problem by remembering, or by seeing, let me see, in the standards guide, in the formula guide, we see that force is equal to, I'm going to be using this one right now, force is equal to the change of momentum over the change in time. Let's scroll down and plug that in right here. Force, which is in this case 750 newtons, is equal to the change in momentum over the change in time. The change in momentum we just calculated, 0.36 Newton seconds, over the change in time, which is what we're looking for, right? So the time taken to stop is that change in time. If it's equal to 750 newtons, that means that by some cross multiplication, if maybe I will have to multiply out for you, I guess, just to make it super clear, maybe it will 750 newtons. I multiply both sides by delta t, and then I would divide both sides by 750, and I would be left with the final answer now of 0.36 over Newton seconds over 750 newtons is equal to 0.36 divided by 750 is equal to 0.00048. So we have the change in time is going to be must be equal to 0.00048 seconds. The newtons also canceled out. Okay, so we got the change of time as 0.00048 seconds. Therefore, calculate the distance that the bullet traveled. And now we could use one of the formulas from A1. Namely, we could use the fact that distance traveled is equal to u plus v, where these are the start and end velocity divided by 2. Assuming that there was a constant acceleration, which there was here because we had this constant force of 750 newtons applied. So that means that the loss of velocity should be a constant. The acceleration was a constant. That was we're multiplying the average velocity now times this is the formula, which is given to you in A1 part of the formula guide. And we can just plug in, we have all these numbers. Distance is equal to the initial velocity, which was 180, plus the final velocity 0 over 2, times 0.00048 seconds is equal to 90 times 0.00 times 90 times 0.00048 seconds, which gives us a final answer of 0.0432 meters. So that is how far the bullet entered into the wall, which was resisting with a force of 750 newtons, which led to a change of momentum of 0.36 newton seconds. Right? So that was C, B, and A of this problem. And a nice little review of momentum, impulse, and some kinematic expression here, the formula for distance traveled when we have a constant acceleration. All right, nice little review. If you're able to do it yourselves independently, good going, you're on track and you're doing well. And we will meet again now for the next topic. I think we'll still be in A2, but we're coming to a close. We're coming to the end of the A2 standards. See everybody for the next video.